The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good morning. I guess I can utilize this time to talk about some things that I always wanted to mention, but I don't know if I had the time. Rehabilitation is a tough subject because I was the chairman of ACI 364 for 10 years, and I almost created a document parallel to 318 for rehabilitation design. Peter Remmons and all the big people were involved. We spent for 3.5 years trying to create this document, and unfortunately ACI wasn't ready to really publish. They always felt that there was a lot of responsibility involved in terms of taking responsibility for rehabilitation and repair. But the biggest problem with rehabilitation is that if something goes wrong, you are completely on your own, because there aren't any documents who are going to support what you're doing, because along the way you're making every decision which is based upon your experience. And how do you justify experience? By having other experts come in and will tell you, oh, I would have never done it that way. Obviously, once it failed, that other person who comes in as an expert, he's always going to testify he's never going to have done it that way. So I think it's extremely important. What I have done over the 50 years that I have been involved with this field, I have always worked with the client, owner. He is your best defense. So what I'm going to discuss here, and I've taken a project which is amazing project, 109 years old, and it was built in 1909. And so I think we're going to, the project of course is structural evaluation of dome at the Cathedral of St. John the Devine, located in New York City, Amsterdam Avenue, 110th Street. And you can see the inside of the church. So that's the inside of the church, and the dome is right up there, way above, about 155 feet up. That's what the dome looks like. The dome was designed and constructed by Spanish architect engineer. His name was Guastavino, Rafael Guastavino. And he and his son were involved, and they built, and you will see further up, oh my God, amazing amount of structures. The son went to university, became an architect and engineer in Barcelona. And interesting thing is that the same professor who would later teach Gaudi, I'm sure most of you have heard of Gaudi, who built a beautiful church and a lot of other stuff. And he moved to US, the Guastavino team moved to US in 1881. And his first major project was Boston Library. If you ever get a chance to see that library, the work that basically he became a tile expert. And his first project, now his son had no education whatsoever. Guastavino Jr. His only education was the first project that he did with his dad, 70-foot span tapered church dome in 1895 at the age of 23. And the dome was 4 inches at the top, 6 inches at the bottom, and the span to thickness ratio of about 200. The entire dome was built in 9 weeks without any formwork or supporting system whatsoever. What was his system? He created masonry shells. He used ceramic tiles, 6 by 12 by 1, and most of his structures were 4 inches thick at the top. He built domes, shell type of structures. But the shell theory was not that known in those days, and he basically used membrane theory approach in designing his structures. The reason he could do building from outside in, 1 row of tiles at a time, because all he did was he took these tiles and joined them with mortar or plaster of Paris, which dries very quickly. He built the one entire line around the wall, built the second one, then set on top of that one and built his second row on top of that. And he also provided fire resistance because of the ceramic tiles. Some of the structures he built: Riverside Church, St. Thomas Church, Church of the Heavenly Set, New York, Boston Public Library, Grace University Church, Nebraska State Capitol, Smithsonian Museum, Washington, D.C., and of course one also in Girard Trust Company building. So he did buildings, churches, auditoriums, all kinds of stuff. The junior built over 600 projects without having an engineering degree in 40 states of the United States. They are all functioning well and in excellent condition. So let's look at this dome. This dome, Guastavino, the church was building up there, the archdiocese were building the church. They ran out of money, not very unusual, I guess. And they went to Guastavino Jr. and said, we want to just build a temporary dome which will last 10 years. And so that we can at least have the church completed. This dome is 135 feet in span. This is the largest dome Guastavino Jr. ever built. It's 155 feet up in the air, 4 inches thick at the top, 12 inches at the supports. Built, he only used cables to work with the geometry of the dome. Otherwise, he had no other supporting system throughout the construction of the dome. And it took 15 weeks. It took exactly 15 weeks. He had a contract to finish the dome by July 1st. Now, one of the things in rehabilitation or in this kind of innovative design is that if you want to work with the owner, you got to start working. First, convince the owner of your innovation, and then start working with the owner from very beginning before he writes the contract for you to do the work. Because once he gives you the 35 or 100-page contract, you already lost. And it's very interesting when we go ahead and see what. This is the drawing, original drawing that I use to actually do my analysis, which comes up later on. He also understood, basically his design was based upon compression. He was going to make these domes, and from the design he found out that he obviously cannot take tension through these tiles. This is not only, this is even worse than concrete because you have so many pieces of, separate pieces of tiles that you're working with. So basically his concept was to make sure that there is no tension in the dome. Only place he would put some reinforcing was near the ends. Now in this case, he at the 4 corners, he had put in some reinforcing. Now here is the copy of the original contract, written in 1909, signed in April. And it was a 2-page contract. And it basically included 4 major items. One, what he's going to do, he said that he's going to construct the floor, the 4 pendatives over the crossing, a temporary roof dome over the crossing, and provide some finish to the arches in case he gets any disturbing to the arches. He was going to finish this on July 1st, 1909, and he was getting paid $35,100 for this entire construction. Here is page 2 of the contract. And even in those days, people understood, what if you don't finish on time? So his contract said that he will be liable, if he doesn't finish by July 1st, 1909, he'll be liable to pay $10 for every day that he is delayed. And then the payment item. The payment said that to make the payments as follows: monthly 85% of the value of the work set in place, plus 50% of the material delivered but not set, save material to become the property of the owner. That's the entire contract for this work. There are some of the pictures of the construction. These are the main arches, the 4 arches, and this is the pendantons that he is starting to build now. And here is dome half completed, and if you look close enough, here is a guy sitting on top of the tiles. Once again, this dome was built without any formwork, any shuttering, nothing. He built a layer of tile, one at a time, and the masons sat on top of the tile he just completed and built the next layer, and the next layer, and the next layer. And that's how the entire dome was completed. Here is a little more completed picture of the dome. Now the dome is fully finished. These are the pendants. These are the arches. The reason they ran out of money, because this is the tower they were supposed to be building, but they didn't have the money, so they ended up with the dome Guastavino, who Guastavino built for them. In '69, we received a call from the Archdiocese that they wanted us to do the analysis of this structure because some pieces of tile and mortar were coming down on the floor. And at that time I worked with Prager Kavanaugh Waterbury, was retained to investigate the existing condition of the dome, evaluate its structural adequacy and integrity, and provide recommendations and repair procedures. So we went out there. First thing to do was to do a survey, and we found there were cracks. These 2 were the major cracks, and you could, by this time, you could even see these cracks from underneath. Basically, these cracks actually started above, outside, and the water leakage and everything else was taking place. Other cracks that were there were around the arches. All these things were cracked. The dome was cracked right at these arches. While I went through and looked at the drawings, I went through the archives and went through the entire history of the dome maintenance since construction. In 1917, first cracks were already reported. Not too bad, 10 years life, so it was only 8 years, but in 37, repairs included addition of a continuous. Now this is where I think my dear friend Guastavino Jr. had a cold feet. He really didn't have to put this ring, but you'll see why this ring became the culprit, unfortunately. 1943, roofing was removed, and old cracks regrouted, new roofing installed. 56, structural evaluation indicated the dome was structurally sound despite the fact that the chips were coming down on the floor. 60, dome was re-roofed, water intrusion continued. 61, Professor Finch from Columbia suggested that this dome be taken down. And in 37, Guastavino himself actually, when he put that ring around, he himself even said that maybe this dome should be taken down. So our job was now first to evaluate this dome. So the loadings were really very simple. The basic loading was the static load plus the rise in temperature in the summer and the drop in temperature in winter. Inside of the dome was heated, so the summer difference was about 30 degrees. Winter, the difference was larger because it could get up to 0 degrees outside. So you're looking at about 70-degree temperature difference. So we started the analysis. The first analysis was where everything is supported. The arches are supporting the dome and the 4-point supports at the indentons. And we did the analysis. We didn't find any tension. Everything looked good. I don't know why it was developing cracks. So, because we had found that the cracks were all around the arches, one of the reasons for this crack was that the arches were very solid in inertia. The dome was very flexible. So as the winter came and the dome started contracting, it separated from the arches. So the second analysis was just assume the support only at the 4 corners, and we applied the loads. Still no problem. Everything was good. Everything was almost in compression. We computed the meridian and hoop stresses at the top of the dome, at the bottom of the dome. Then came, so now we are thinking, what is happening to this dome? We went out there, we went up to look at the ring, all the way to the top, and then I modeled the ring into my structure. And that was the culprit. Once we put the ring in, the support became a lot higher. And that's what created the tension and the tension cracks. So here are the stresses. These are the meridian stresses, and you could see this is all the tension, and they were in the value ranging way above the modulus of rupture that we could compute for this composite material. These are the tensile meridian stresses in the inside of the dome, and the value of these stresses were much smaller compared to the other outside dome where they were very large values. Then tensile hoop stresses. Now because there are tiles and the layers, the hoop stresses we found they were actually carried through friction through the various layers of tiles. So the hoop stresses were not really causing any significant problem with the structure. These are the tensile hoop stresses on the inside of the dome. And these are the meridian stresses which actually cause the problem. And the problem was basically in this area. Everywhere else, it was in compression. And the problem was basically in this area. So now we analyze this dome. The question was, what are we going to do? There was a tremendous pressure to bring this dome down, and particularly Columbia, professors saying that it must be brought down created a lot more pressure on the engineering community. There were 3 or 4 other consultants. There were 50-50 opinions. Major consultants were involved, but the consensus was to bring the dome down. So we went in, had many meetings with the church, archdiocese, and we said that we should keep this dome. The only problem with this dome, twofold. One, the temperature differential is causing basically the loading. What if we reduce the temperature differential? Very simple solution. And what we came up with was to put styrofoam on the outside of the dome, thick styrofoam panels, doesn't add much weight, and then re-roof the dome above it. And the inside problem was pieces coming down. That can perhaps hurt somebody. So we came up with the idea of putting a metal netting inside the dome so that we will not have any pieces coming down. So basically we said, of course, introduce these sheets, or actually cubes. They were about 3 to 4 inches thick, and provide netting. And we did a lot of other repairs. We've grouted the cracks and a lot of other repairs that we had to do. And the dome is still there. I was there 2 years ago to listen to a Christmas concert. And this is what the dome looked like much closer. This is when we did the repair, putting the netting. And you can see what it looks like close up. So what the lesson is, you got to work with the owner. If you're going to do rehabilitation engineering, don't listen to the architects. If you're doing a private client, go directly to I have about 8 other projects. Hopefully if I survive, I'll present those to you. But it's very important to work directly with the owner, because if you don't, you are going to be sitting in that chair and somebody else is going to tell you, I would never do it that way. Thank you.